Today we're doing 4.2, relative extrema, first and second derivative tests. 4.21 definition says, a function f is said to have a relative maximum at x0 if there is an open interval containing x0 on which f of x0 is largest value, that f of x0 is greater than f of x for all x in the interval. Similarly, f is said to have a relative minimum at x0 if there is an open interval containing x0 on which f of x0 is the smallest value, that is, f of x0 less than or equal to f of x for all x in the interval. If x has either a relative maximum or relative minimum at x0, then f is said to have a relative extremum at x0. What the 4.2 definition is saying, for any value on f of x, there will always be a maximum minimum. It just depends on if it's relative or minimum. For example, this would be an absolute max because it's the greatest point on the graph without anything going up above. Then this would be a relative min because it's going down farther in both directions, but we don't know those actual values. But for a closed interval from here to here, it'd be absolute, but on the open interval it's relative. And then we have a relative max up here because on the open interval it's lower than the absolute value over here. On the next graph we have a relative max and a relative min because in both directions it's going higher or lower, and we just don't know those values. We have an absolute minimum here and a relative max here. And then we have an absolute max here and an absolute minimum here.
2.2 theorem. Suppose that f is a function defined on an open interval containing the number x0. If f has a relative extremum at x equals x0, then either f prime of x0 equals 0 or f is not differentiable at x0. The values in the domain of f at which either f prime of x equals 0 or f is not differentiable are called the critical numbers of f. It is important to note that Theorem 4.2.2 does not guarantee that these critical numbers result in a relative extrema. They simply provide all possible locations of relative extrema. So if f prime of x equals 0, that's a critical number. 4.2.3 theorem, first derivative test. Suppose f is continuous at a critical number x0. If f prime of x is greater than 0 on an open interval extending left from x0 and f prime of x is less than 0 on an open interval extending right from x0, then f has a relative maximum at x0. So x0 would be the relative maximum. If f prime of x is less than 0 on an open interval extending left from x0 and f prime of x is greater than 0 on an open interval extending right from x0, then f has a relative minimum at x0. So x0 would be the relative minimum. If f prime of x has the same sign, either f prime of x is greater than 0 or f prime of x is less than 0, on an open interval extending left from x0 and on an open interval extending right from x0, then f does not have a relative extrema at x0. So x0 would not be a relative extrema. You use the first derivative test to locate the relative maximum and minimum of f of x. So when you find the first derivative, you get 4x to the 1/3 minus 6x to the negative 2/3. So then you can factor out a 2x to the 1/3. So you get 2 minus 3x to the negative 1 in parentheses. And you set that equal to 0. So 2x to the 1/3 equals 0. So you get x equals 0. Get 2 minus 3 over x equals 0. You have 2 equals 3 over x you multiply by x on both sides, and you get 2x equals 3, and x equals 3 halves. So then you do an interval test to find out if 3 halves is a maximum or minimum. So you can do numbers like 1 and 2. And when you plug 1 and 2 into the first derivative, you get negatives for both. And when you plug it into the original equation, so you know that you have a relative minimum at x equals 3 halves.
Okay, locate the relative maxima and minima of f of x equals 1/3 x cubed minus 6 halves x squared plus 9x minus 5. So first off, you have to find the first derivative, and when you do that, you get x squared minus 6x plus 9, which factors down to x minus 3 squared. And then you set that equal to 0, and you're going to get x equals 3. And so then when you graph it, you're going to have at 3, you're going to have it 0, showing that it's not a relative minimum or a maximum, it's just an inflection point. And when you do the interval check 3, it's going to be positive on both sides of it, meaning that it's not a relative maximum minimum. So you would just write relative max or min do not exist. That's how you would finish that problem.
4.2.4 theorem, the second derivative test. Suppose that f is twice differentiable at x naught. If f prime of x naught equals 0 and f double prime of x naught is greater than 0, then f has a relative minimum at x naught. If f prime of x naught equals 0 and f double prime of x naught is less than 0, then f has a relative maximum at x naught. If f prime of x naught equals 0 and f double prime of x naught equals 0, then the test is inconclusive. That is, f may have a relative maximum, a relative minimum, or neither at x naught. So to locate the relative maximum and minima of f of x, you need to find the first derivative, which equals negative 2x minus 4. Then you set that equal to 0. So you get x equals negative 2. And then you're also going to find the second derivative of x, f of x. So you find the derivative of negative 2x minus 4, which equals negative 2. And then you do an interval test. And be positive in this interval, negative in this interval. Therefore, you have a relative maximum at x equals negative 2.